Regularization. Regularization is the technique used to control overfitting in machine learning. In the previous lectures, when we saw curve fitting examples, that is, when we were fitting curves like this, we'd seen that when we chose higher order polynomials, that is, when we tried to choose complex models in order to learn this curve, it tried to overfit. So this is a common problem in machine learning, that when you try to model something using a complex machine learning model, it will try to overfit to the training data. It will try to learn the exact features of training data, which would mean you would fail to learn this underlying regularity. Instead, you will learn to fit exactly with the training data, which would mean if you give any data which the model has not seen before, it would give very wrong outputs. For example, let's just draw the curve that we drew in the last lecture and start learning from there. Let's say this is the curve that you want to fit. This is the curve on which you want to fit. Let me darken it a bit. So this is the curve, let's say, on which you want to do curve fitting. And you have a few points here and there on this curve. You have to learn this curve from these points. So your model is supposed to learn from this, right? Let us say these are the points. What happens if we are ideally expecting it to fit exactly with this curve? So anything close to that would be a good model. But what happens is, if you choose a very higher order polynomial, let's say power of the polynomial is equal to 10, which would mean your equation would look something like this. Y is equal to W0 plus W1x plus W2x square plus dot 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 up to W10 x power 10, which means this polynomial has 11 degrees of freedom. That is, all these w's this model can choose as per its wish. So it has 11 degrees of freedom, and using that, what will this model try to do? It will try to fit something like this. All these points, it will try to go through all these points and find a curve of this kind. See, it won't miss any of those points, which would mean mathematically, if you see the error in your function, that is, how do you normally see the error? Your error is y minus t, where y is what you got from this equation and t is your actual target, that is the actual point. So if you see everywhere, your blue line which corresponds to y matches exactly with your yellow dots, which are your target points, which means your error will almost be 0. So mathematically, your model is perfect as per the training set. But is this model perfect? No. That is, if you, let's say, take any point, let's say corresponding to this value of x, then ideally you should have got it here. But your model would say the point is here, which is wrong. So in order to limit this, in order to control overfitting, you will introduce the concept of regularization. To understand regularization, let us first see what causes this overfit. In the previous lecture, we discussed about that. That is, when the model gets a complex model, that is a higher order polynomial, it will try to optimize the value of W0 such that it will take not just W0, all these W's to such values such that it would exactly fit the dot, which would mean these W's would take very high values, like this value of this particular equation would be something like 9387 plus 10,121x plus, like this. So all these W's will be taken to very high values so that this equation can exactly fit all these dots. That is all your data points. What should be done in regularization so that you can limit this? Just think, what should be done? Conceptually, logically, what should you do? You need to limit the value of w's. That is, you should not allow w to go to very large values. If this happens, your curve, instead of looking like this, your curve would look something like this. See, instead of this, your curve should be something like, let's say, oh, I didn't choose the green color. Let's say I chose this. And instead of this blue curve, your curve would come to something like this, which is the ideal scenario. Let's say it would be something like this, somewhat a close approximation of the yellow line. So to make this happen, what you have to do, you have to limit the values of W. You want to ask W to take smaller values. What will you do for that? That is the concept of regularization. You will add a penalty term. That is, you will penalize whenever W takes larger and larger values. Let us consider the sum of squares error. Sum of squares error, how did you calculate? Error was sum of squares. That is, you will sum, let's say there are n data points in total. From n is equal to 1 to n. What will you do? Your error term is y minus t, where y is what you observe from your the line that you make, y of xn w minus tn. This was your sum of squares term. In order to make sum of squares, you have to square this. So why am I writing capital W here? That is, in our equation we had W0, W1, W2, so on. Now this capital W, this is the vector which has all these terms, right? W0, W1 up to Wm. This is capital W, right? So this is your sum of squares error term. This is your error term. What will you do to this error term to make sure that your W's will not take higher values? You have to add a regularization term which would penalize any higher values of W. So you will add lambda by 2. This lambda is your regularization constant. So the regularization parameter. To this you will add square of this, square of W. So now what happens is, along with your sum of squares error term, you added your sum of squares regularization term. What will this do? If whatever be the value of W, you are adding square of that into the error term, which means as W take higher and higher values, automatically your error is going to increase. So what will your linear regression try to do? Your regression will try to make error 0. It will try to minimize error. So as the value of W increases, your error is automatically increasing once you add this regularization term, which means your minimization of error condition will automatically make sure that the value of W is not going very high. It will limit it to a moderate value where you can have a lesser error with lesser values of W, which means you will get this green line instead of this blue line. This is the whole concept of regularization. So here, this lambda is what governs the relative importance of regularization term. That is, how much importance should you give to increasing the increasing values of W, and how much importance should you give to your actual error term. This is decided by this regularization term called lambda. So lambda is your regularization parameter. Now this particular regularization, in which you use the second order term, the quadratic term, this is called L2 regularization. L2 regularization. And one more thing, what is this square mean? That means W transpose W. That is, I already told you W is the vector of all W's, that is W0, W1 and so on. So what will W transpose W give? That will give you W0 square plus W1 square plus W2 square up to, let's say there are mth order up to mth order polynomial, that Wm square. So basically it is a sum of squares. This is why it is called sum of squares. See here, in order to make it sum of squares, you had to add a sum term. But here when I said I am adding sum of squares of W, I didn't add any summation here. Why didn't I add any summation? Because this inside it already have the summation, because your W is already a vector. Your W is a vector like this, W1, W2 up to Wm. And now when you do W transpose W, what happens? It will have a sum of square. It will automate by default do sum of all the coefficients. So you have a sum of squares error term on the left and a sum of squares regularization term on the right. What is it that you have to be careful of while using this regularization? That's what we'll see next. So while using this regularization term, this is what you have to be careful about. First thing, Previously, I told you that you have to carefully choose the value of m. Now I'm telling you that according to the complexity of problem, you choose a value of m. That is done. You choose a model, you choose the value of m, but in order to control overfitting or underfitting, you have to choose value of lambda carefully. That regularization parameter should be chosen carefully. What happens if your lambda is high? If your lambda is high, it will automatically make sure that your W is low. That is, all your coefficients would go lower. What if you make lambda very high? Let's say you chose a very high value of lambda, which means your coefficients will all approach 0. All your W's will go to 0. What happens if your W is 0 in the equation y equal to W0? 1 minute. What if in this equation y equal to W0 plus W1x plus W2 x square? Let's say there are a lot of higher terms as well, up to Wm x power m. If all the W's are almost 0, your y will almost become the line of y equal to 0. What is y equal to 0? The line through the x-axis, that is this line. This will become y equal to 0. So this won't have any ability. One more thing, that is, normally in the regularization term, you will try to avoid this W0 from being included, because the problem is, if you include W0, what happens is, it will decide your intercept, that is your origin. That is, for example, if you take this term, ideally if you make all W0, you should have the ability to choose any of the y equal to W terms. That is, it can be y equal to 1. You can draw a line here or here, here. At least this much of freedom you should have. Otherwise, what will happen? Your W0 will decide where your line should meet the y-axis. So this will become a limitation. For that reason, normally in regularization term, you would not add this W0 term. You will only add the remaining W's, right? In the regularization term, I'm saying, that is in this term. So this is the equation. Okay, so it is clear for you now that using regularization, we can control overfitting, but you have to be careful of lambda causing overfitting or underfitting. That is, if the value of lambda increases, there are chances of underfitting, right? And if the value of lambda is small, there is a chance of overfitting. So you have to choose a decent value of lambda. A value of lambda which would avoid underfitting and overfitting. So now the whole problem boils down to choosing the right value of lambda, and that you will do by choosing the right validation set. And in validation set, you will try out different values of lambda and find whatever is the perfect one. So we'll go into training set, validation set, test set and all in the coming lecture.